Okay, so this is the second topic on electrochemistry and effect of concentration. And this has something, has something to do, what we call the Nernst equation. And in the bottom, I have shown you, and this is a copy and paste of the exam reference sheet. And the Nernst equation is something shown up here. Okay, this is a little funny notation, and this is usually just people write an F. That's a Faraday constant. It's very important to understand the concept of Faraday constant, and I'm going to actually explain it here before actually I'm going to solve the problem. F is a Faraday, which is a very important electrochemist and chemist in general, and the F is a Faraday constant, and it is nothing but 96500 coulombs per mole. And to be more exact, a mole of electrons. So actually, when we have collected 1 mole of electron has its own charges, right? And you guys can look at the charges of electron, and the total charge will be F. Okay, so you can imagine now the simple relationship. The Faraday constant, 96500 coulomb per moles of electron, is essentially the same as Avogadro's number times charge of a single electrons, right? So which is this one will be a unit of a coulomb, and then there will be Avogadro's number with 6.022 10 to the 23. So now you guys actually can get this reversely calculated. Charge of a single electron will be Faraday constant divided by Avogadro's number, okay? And there will be a coulomb per 1 electron. One electron, I guess, do you want to say 1 electron particles. At any rate, so let's solve this problem with the Nernst equation. So Nernst equation, I'm going to write it one more time. The actual cell from this galvanic cell is electropotential from the standard state minus NF RT ln Q. Okay, so that's the Nernst equation. In here, in this problem, the Q is, there's nothing really in solution except this one, so the Q will be Cl minus concentration in terms of molar concentration. So all you got to do is simply plug it in and then trying to find out. So this one has a standard potential, which is 1 molar concentration. That means actually the standard, which means this notation. So this will be a E cell naught, and then they put it into a solution containing an unknown concentration of chlorine. So this is what we want to find out, chlorine, and the cell generate this much of the cell potential. So that's what we are measuring. Okay. So once again, I'm going to write the Nernst equation. NF, RT, ln Q. So now this is a Faraday constant I talked about before, and that's a gas constant, that's a temperature in Kelvin, I think you know. What is an N? N is essentially number of electron involved in the reduction and the oxidation reaction here, and from the half reaction. So this is a case when N is 1 electron per reaction is relayed. So in this particular problem, N is 1, right? So I can write it as 0.0478. Standard one is 0.2223, and the minus 8.314. And what's the temperature? And the temperature is not given, then it is 25 degrees C, which is 298 Kelvin. Okay. Sometimes people forgot to mention they specify the temperature. Then you can just assume that 298. That's a room temperature. Okay. And then the number of 1 is 1. The electron involved in this reaction is 1. So there's a 1. And then 96500 coulomb per mole. Okay, and then Ln, concentration of chlorine minus. Okay, so I just need to solve this problem. Okay, all right. So when I solve this problem, you will see that minus 6.797 is natural log of chlorine minus. So chlorine minus is exponential 6.797, and that will 1.117 10 to the minus 3 molar concentration. Okay, so that's how you solve it for essentially effect of concentration. So let me recap this, what this Nernst equation means. This Q portion is essentially depending on the concentration of various electrochemically active compound, and so that therefore how much they are deviating from the standard state to a different one. Okay, different actual voltage depending on the concentration scenario and each reaction condition.